Okay, welcome to note set number 19, where we're going to get into the details of the Dtft. In the last lecture, we motivated what it was, saw where it came from, and waxed philosophical about how wonderful it is and all the great things that it will allow us to do. Now we need to bury ourselves in some of the mathematical details of this thing so that we can learn a little bit more about it. So what we've seen is that the conceptual CTFT, so I say conceptual there because really it's not something that we can actually compute. We just use it as a concept to think about how our systems will behave, find frequency responses of systems, and visualize what those things are going to look like. But as far as the CTFT of a signal, unless it's a textbook thing that's on our table, we can't really do much with it. But we now have this thing called the Dtft that looks like we have a chance of actually computing it from samples, and that's exciting. So this is how we defined it before. We have the Dtft. It's a function of capital omega, which is our discrete time frequency with unit of radians per sample. Notice that omega times n is our sample index, so it has the units of sample, so to speak. So we have radians per sample times sample gives us radians. So that's an angle that has to be there in radians up in the e to the j blah. Anything that shows up e to the j blah has to be in radians. So we're good. So that's what we had last time. Compare this to the CTFT and we can see some very similar structure. We have a signal multiplied by an e to the minus j thing with a frequency, with a time variable. In both cases, the units up next to the j are in radians. Here this unit is radians per sample. Here the unit is radians per second. And here we have a sum, and here we have an integral. So just remember that an integral comes from sums. They're just quote unquote overheated summations. And so this really shouldn't surprise us that these things look very similar. And furthermore, shouldn't surprise us that they have very similar properties. There's a few things that are different, but more things that are similar than are different. Now, before we get too much into this, let's just see if we can figure out analytically what a Dtft of a particular signal might look like. So here's one. It decays down exponentially here for a little while and then goes to 0 at some point. I'm showing this here for q equal to 3, but we can do it in terms of a general q. Actually, it looks like I'm doing it for q equal to 4, actually, in this example here. This is something that we're going to do analytically, meaning with our brain, not with a computer. So notice that if A has a magnitude less than 1, this thing will decay down. But if A is greater than 1, this thing will explode upward, but then hit 0. And if A happens to be less than 0, this thing flips sign, positive, negative, and so this thing will actually oscillate. So the picture that I show here is just one example of what this thing might look like. So given this signal, find the Dtft. So there's our definition of the Dtft. Since only a finite number of these elements are non-zero, this finite sum is going to become, or this infinite sum is going to become a finite sum. And it's going to run from n equals 0 up to q, so just over this range where things are non-zero, during which the signal is equal to a to the n. Now we use a property of exponentials and just combine these two exponentials together like that. And then we use a thing called the geometric sum. You can Google that if you want and find more information on geometric sum. It shows up a fair amount in this discrete time signal processing stuff. But it gives us a closed form for this sum. Closed form means a nice formula that you tell me what R is You tell me Q1 and Q2, and I can just plug them in and I get a number rather than having to explicitly evaluate the sum. Okay, so I use that geometric sum result with a little bit of further manipulation, and I get something that looks like that. So here's my function of omega, and I can see how it depends upon Q. I can see how it depends upon A. So there we go. We found our first DTFT by hand. Now, most of the time, just like with CTFT, we won't be doing these complicated summations and evaluating them with math tricks. We'll be using a table, and there's a corresponding table for DTFT. I encourage you to take a look at it. And then there's also characteristics and properties of the DTFT that are on that table as well. So let's talk about a few of these characteristics right now. So one thing is the periodicity of x of omega. So we've already seen in these pictures that we've been doing with our beloved triangular spectrum, we've already seen that there are these spectral replicas that show up, and those continue on out as far as minus infinity, plus infinity. So this is on our omega axis, and we've seen that that was centered at 2 pi. This is centered at minus 2 pi. And so we see this 2 pi periodicity. And so all that means is that if we offset omega by 2 pi, we get exactly the same value as having not offset it. So pick a value of omega, go 2 pi over, you'll have the same value. And so since the function itself is periodic, that periodicity carries over to the magnitude as well as to the phase plot. In general, just like the CTFT, the DTFT is complex valued, and that comes from the fact that this thing is complex. Now, there are situations where x of omega turns out for that example to be purely real. Sometimes it's purely imaginary. But in general, it could be complex. So we need to think about its magnitude and its phase. So just like we saw for the CTFT. Notice this periodicity property is unlike the CTFT. So we've seen one thing that's the same and one thing that is different. Another thing that's the same as CTFT is the symmetry properties. So if our signal is real valued, then we have even symmetry on the magnitude and odd symmetry on the phase. So that's exactly like what we saw for the CTFT as well. Now we've seen inverse CTFT. We have an inverse for the DTFT, and if you look at this and compare this thing to what we had, the equation for the inverse DTFT, you'll see, or the inverse CTFT, you'll see that it looks almost exactly the same. The only difference is we only have to go from minus pi to pi, whereas for the CTFT we had to go from minus infinity to infinity. This says, why do we have to go outside there? The stuff outside there is just replicas of that, so we can get all the information that we need from within minus pi to pi. So that's pretty straightforward. We had generalized DFT or generalized CTFT for periodic signals, and if we happen to have a discrete time periodic signal, then we will have DTFTs that contain delta functions. For example, x of n equal to 1, that's a degenerate periodic signal. Technically it is periodic. And if we were to take the DTFT of that, we would find out that it's a delta function. Now the interesting thing about this, here's a plot of it that's telling us here's that delta function at 0, and we really only need to look from minus pi to pi. And so all these out here are just the spectral replicas, the periodicity part of the DTFT. So what this is telling us is the same thing for CTFT. Fourier transform of a DC signal, a constant, is all concentrated at 0 hertz for CTFT, 0 radians per sample for DTFT. So that makes a lot of sense. Now, another way of writing this, and this is common in books and on tables, is to write, instead of writing it like this and saying, here's what it looks like inside minus pi to pi, and then telling you that it's periodic elsewhere, you take the thing that's inside minus pi to pi and shift it out to create all of those replicas and then add them all together. So this is a very complicated way of writing things, and it tends to get students into a fair amount of trouble. So even though the tables tend to show it that way, you should learn that when you see this kind of thing where you've got a sum and you've got this mechanism that's creating replicas that are spaced 2 pi apart, you can just say goodbye sum, goodbye replica creating machine, and that's what I really have. Okay, so you need to learn how to do that and visualize that. Then just work within minus pi to pi. To derive this result, let's work backwards since we have a prospective result for this case. We would be doing the inverse DTFT here. We're integrating from minus pi to pi. Replace that by the single delta function inside that region. Now we use the sifting property. We sift this thing, replace omega by 0. That becomes 1, and we're done. So that tells us, sorry about that, that tells us how to derive that result. But the more important thing is to remember that a constant discrete time signal transforms over into a delta function at the origin. Now, what I'm showing here, aside from being a vision test, you have these tables. It's the DTFT table on the left and the CTFT table on the right, or what we've been calling just the Fourier transform table. And I've drawn arrows showing the same entries, and you can see that some of the entries are missing. It's not because sometimes it's because they don't exist for one case or the other, but it's more likely just that it got put on one table and not on the other. And actually I see that I missed an arrow. There should be an arrow there. Those two are the same. So down here you can see there's one of those that has that summation and replica creating machinery. So instead we can think about the sink really just transforms to a rectangle, just like before for the CTFT. So I would encourage you to get these two tables, put them side by side, compare and contrast the entries, and learn for these bottom entries here. You really need to learn how to deal with interpreting those sums and all of these replica generating machinery so that you know how to visualize that properly. So let's find the DTFT of a rectangular pulse. So remember, this Q here tells us the extent that the pulse goes, not the width like in the CTFT case. So by definition, we plug that mathematical equation into our DTFT formula, and we end up with a finite sum that looks like this. And again, using the geometric sum result, we can evaluate it like this. And then, do I show the steps? No, well, the book shows the details. But basically, you go Euler hunting. You go hunting for Euler. So you can pull out some exponentials and things here to turn those things into signs, and so we get something that looks like this. Now this looks sort of like a sinc function, but not quite. A sinc function is sine of pi x over pi x, but remember, for small angles, sine of theta for small theta is equal to theta. So at least near DC, near zero values of omega. So for small values of omega, this thing looks an awful lot like omega over 2, and we start having a sinc-like behavior of this thing. So we can sort of think of this as a discrete time modification of the sinc function. Okay, so we've seen a few examples of Dtft. Again, I encourage you to pore over your Dtft table to make sure you know those. But there's also a lot of properties. We've seen properties for the CTFT, and we have similar properties for the Dtft. Most of those properties are identical, but there are a few distinctions. There's a summation property that replaces the integration property, and there's no differentiation property and nothing that works kind of like it. So keep in mind that. As far as properties, the most important ones: time shift, modulation, convolution, Parsifal's theorem. Those all are virtually exactly the same. Sometimes we have to account for this minus pi to pi and the periodicity part of it, but they're all pretty much the same. So you should take a look at those. And again, here I have the two tables for the properties laid out side by side, showing which ones correspond to each other. And so you should be aware of the similarities and the differences. Now there are a few here that we have to talk about separately. So this result down here is what we'll be talking about on the next slide. So suppose we're given a rectangular shape in the frequency domain. So this is a Dtft. It's omega. Here's our x of omega. We're looking at it from minus pi to pi, and notice that we're showing the replicas, and we should put dots out there to indicate that this continues on. If we don't have those replicas out there, if they're really not there, then it's not a real Dtft. So for us to say, let's look at a rectangle Dtft, we're talking about a rectangle in minus pi to pi, and we better be thinking about there being other rectangles out there to make it periodic. And so we want to find the inverse of this, to find what time domain signal has this as its Fourier transform. So we look on our table and we don't see it there, and but we can use this property, this last property on our table, relationship to inverse CTFT property, and there's 4 steps. The first 2 are listed here. So that the idea is you truncate to the minus pi to pi region. So we get rid of this and we get rid of this, and we imagine extending the 0 out forever. Okay, so we just multiply by this rectangle, not because there's a rectangle here, but because that's the mechanism by which we zero these things out. So now we treat this thing as a function of omega, but with still the same markers, right? B, pi, 2 pi, and so on. So we're just changing the symbol, not doing a unit conversion. So those are the first 2 steps. The third step says, look this thing up on our CTFT table. So we go back to this thing and we say, oh, it's a rectangle as a function of omega with a edge at b, width of 2b. Okay, I got it. That's a sinc function. Write out what that is from the CTFT table. Okay, so that's right off from our CTFT table. And then convert it into a Dtft result by replacing everywhere there's a t, replace it by n. So that t gets replaced by n. So this is the signal whose Dtft is that rectangle that we started with, and obviously there has to be the replicas. So that's a really nice result, a powerful property that allows you to draw over results from any CTFT table and make them DTFT results. Now I should say there are a lot of results already that are duplicated on those two tables. They come from this property, so you should be able to actually do some examples of this yourself and check them on your two tables to see that you got them right. So let's take a look at the DTFT of a discrete time sinusoid. So here is cosine of omega 0 n. Now remember, we limit our omega 0 to be between minus pi and pi. That's our beloved minus pi to pi range. So how are we going to find this? We have everything we need. We can imagine there being a 1 out in front being modulated by a cosine to create this signal. And we know what the Fourier transform of 1 is, and we know how to work the modulation property. So by using that, we know that this thing here, if we define that to be y of n, we know that that has a delta function at the origin. Okay, let's get rid of all this extra machinery. Oh yes, a delta function at the origin. So there it is with the replicas that all this machinery was creating. So that's the thing that we're going to be modulating to create our desired signal. And so now this thing is going to shift it up and down by omega 0. And remember, omega 0 is between minus pi and pi. So that's just saying another way of writing that result. And now we're going to shift it up. So the modulation property says shift up and down. And so now using this easier form, we just take the delta function that was just an omega in there, we shift it up and down, and now we show that's the more complicated form. And we should have a picture here. So there's the thing unshifted, and there it is shifted up, there it is shifted down, but we add the two together, and so there it is. The red and blue together constitutes the Fourier transform, the DTFT of a cosine with frequency omega sub 0. So this makes complete sense again. The DTFT, the inverse DTFT, is trying to build that cosine by adding together a bunch of complex sinusoids. And what frequencies do we need? Well, we need a complex sinusoid at positive omega 0, and we need one at negative omega 0. But only at those two frequencies. That's all we need. Just like we saw for the continuous time. So these last four entries are for the sinusoids, discrete time sinusoids. And again, note that each of them has one of these summations in it that we can ignore, and they have this 2 pi k machinery that we can ignore. If we ignore it, we just have to remember, and it repeats periodically outside of the minus pi to pi. So that finishes our results here for this lecture, and I'll see you next time. Thanks.